Okay, welcome and thanks for being here, everyone. I'm Chuck Friedman. I'm one of the two co-chairs of the Learning Health System Collaboratory. It's a pleasure to have you all here today. And as you can see from this first slide, today's topic is making sense of unstructured data. This session is, in a way, a complement to the session we had last month, which is or was focused on structured data as part of our theme of focusing on data this year. And as such, this session focused on unstructured data will advance us into a new and important direction. Just want to let you know that the session is being recorded and the link will be shared with all of the attendees and registrants. The session will be live closed captioned, and we are going to ask you to post your questions in the Zoom Q&A pod, not the chat, because the chat will not be available to attendees. Attendees who have questions will also be able to unmute to ask their questions live and in person. Well, not quite in person, but almost in person. So next slide, please, Lisa. So as I said earlier, the theme for this year's symposium seminar series is data and the learning health system more specifically. And as I said last month, the presenters spoke about structured data, and we move into an exploration of unstructured data this month, which are the data often buried within free text in clinical narratives. I've heard estimates that the amount of unstructured data in electronic health record systems is greater and somewhat significantly greater than the amount of structured data. And obviously, unstructured data are difficult to analyze and to make sense out of if we are pursuing the goal of deriving useful insights from those data. This session will address two specific techniques for interpreting and converting unstructured data into useful research data. We're going to focus on two related, important, but distinct approaches: natural language processing, which will come first, and information retrieval, which will come next. Next slide, please, Lisa. So the first part of the session focused on natural language processing will feature Vinod Vidiswaran and Zhu Shi. And next slide, please. And the second piece of our program today, focused on information retrieval, will feature presentations by David Hanauer, Leslie Yuan, who is visiting us from the West Coast virtually, and Christina Angelis. Let me introduce them. Go back to the first slide, the previous slide, Lisa, and I'll introduce them in more detail. Vinod Vidiswaran is an associate professor in the Department of Learning Health Sciences and also the School of Information. He studies clinical and consumer natural language processing, information trustworthiness, large-scale text mining and analysis, and medical information science more generally. Zhu Shi is an assistant professor in the Department of Biostatistics here at the University of Michigan. She's broadly interested in developing novel statistical methods that provide insights from high volume and high variability administrative health data and electronic health record data. She, in particular, focuses on developing causal inference methods tailored to EHR data. So Vinod and Zhu will be our two speakers focused on natural language processing. As we move into the information retrieval part of our program, David Hanauer will be the first speaker. He's an associate professor in the Department of Learning Health Sciences here at the University of Michigan with joint appointments in pediatrics and the School of Information. He's the informatics faculty lead for the CTSA-funded Michigan Institute for Clinical and Health Research, also known as MICHAR. He's been heavily involved with development and national dissemination of a variety of information and software resources, including EMERSE, which will be the focus of the session today, which is a self-service tool designed to help research teams find cohorts and abstract data from free text clinical notes. Leslie Yuan, our visitor from the West Coast, is the Chief Information Officer for the University of California, San Francisco, Clinical and Translational Science Institute. She's responsible for a team of professionals who manage, develop, and innovate on technology and infrastructure projects that support the Institute's mission to accelerate translational research. And last but certainly not least, Christina Angelis is an assistant professor of surgery and an assistant professor of dermatology at the University of Michigan. She currently holds a clinical scientist development grant from the American Cancer Society and a clinical investigator award from the Society of Surgical Oncology for her translational research focused on the mechanism and effects of immunotherapy in melanoma patients. So these are our 5 outstanding speakers. Next slide, Lisa. Next slide is question and answer session. We aren't there yet, so let's now begin with our first speaker, who will be Vinod Vidiswaran. Vinod, thank you very much.
Thank you very much, Chuck. Let me share my screen and get started. Are you seeing my slides?
Yes.
Okay, great. Thank you. I will not be monitoring chat during the presentation. So if there's something, please, one of the panelists can unmute and raise attention. That would be great. Thank you very much. Welcome, everyone. It's an honor to kind of present in front of you the promise of unstructured data and the role of natural language processing on health text. My research interests are focused on transforming data into actionable knowledge while addressing the issues of context, scale, and quality. So my work is rooted in machine learning, natural language processing, and text mining. But through that, I study challenges in clinical decision support, medical information extraction, consumer health informatics, and trustworthiness of information. And I'll touch upon some of these today. But all of this is thanks to the efforts of my research group, and this is a group. We had an outing in summer, and this is a picture from there. Thanks to all of you, including the pets who are seen here. Just kind of start off, I do not have any conflicts of interest to disclose, and my research is supported by grants that are funded by NIH, AbbVie, Hensley Foundation, Moody Endowment, Robert Wood Johnson Foundation, and last but not least, internal grants from University of Michigan. Okay, so when we talk about big data or text data in clinical and medical domain, traditionally, people think of books and journals and peer-reviewed literature, and that is an important piece of an important set of information. There are about 31.5 million citations in PubMed. And then you have one order of magnitude higher would be medical records that are in electronic form now. Just from Michigan Medicine alone, there are about 400 million documents, which are these notes and discharge summaries and intake forms and so on that are collected during typical patient care. Another order of magnitude higher would be prescriptions. So for example, just in 1 year in 2019, there were about 3.8 billion retail prescriptions that were filled by US pharmacies. So already we're talking about large scale data that is in text form, but that's not all. There are newer patient-facing information sources, such as websites when someone searches on Google or other favorite search engine online, blogs and forums where peers or patients communicate with their peers and share information, there are community-generated resources like Wikipedia that again come up as high query results when you do a search result. So when you do a search query, and then last but not least, tweets and other newer forms of kind of social media data, even shared by reputed sources and sources of authority. So getting this data and transforming it to knowledge becomes a critical task for downstream clinical decision making. So for example, you would want to take a web page like this, an article that talks about Erbitux helping treat lung cancer, and another one that talks about cetuximab, and infer that the information that this is sharing is that Erbitux helps treat lung cancer. And if you notice, cetuximab is really Erbitux, but it's just a generic name for that, right? So they both talk about the same information, but they're coming from different sources. So that is disambiguation of information. So medical natural language processing takes these forms of data sources, converts it into insights and actionable knowledge. It's not only to understand the language. For example, Tom visited a clinic where Tom is a noun phrase or visited is the verb. That is a part of it. But really through that, to get more insights into what is the sentiment around a particular medication that has been taken, or how do you classify a particular document? What are the topics that are discussed in a clinical visit? These are the kind of basis tasks for natural language processing in health domain. When I was thinking about what to present today, I kind of relied on some work that is happening at Michigan, and through that kind of highlight different tasks of medical NLP. So for example, I'll talk briefly about medical information extraction, on simplifying prescription directions, and understanding community health through social media. You would see these icons throughout the rest of the talk, where I would be kind of highlighting key challenges and projects through those that are addressing some of those challenges. So let's start with natural language in clinical notes. This is a synthetic example, but our clinical notes are not too far away from these. Already, you would see that there are different entities of interest. So for example, you have names of patients and doctor. You have identifiers such as a medical record number. You have dates that are both date of birth, date of service, or other years that are spread throughout the note. You have phone number, email, and then also locations like Mount Sinai where care happened, Jackson where this patient lives, Manny's Brewery where they work, and profession. All of these are what are called protected health information, PHI, right? And through that, understanding these kind of bits of information about a person becomes critical. And if you are sharing this or using it for health services research, this is protected information. And so removing this information from notes becomes a critical natural language processing task that is called de-identification. We'll touch upon that throughout today's session. What about natural language in prescriptions? A lot of prescription written by providers is written in a very cryptic language. So 2 puffs orally Q4 HRS X90 DYSVs. For those who are reading it, you might get a sense of what this is talking about, but it is really difficult for computers to understand this unless we train them to. What they're saying is you have to start making sense of these tokens. The fact that Q4 HRS actually is 3 components, Q, 4, and HRS. And then to kind of understand that that is actually frequency, and 2 is dosage, and puffs is form, and so on. And then finally, the prescription that patients see is really a nicely formatted English sentence that asks them to inhale 2 puffs by mouth every 4 hours for 90 days for Wheezy, right? So this conversion is like a translation of information. Even though it is from English to English, it is really professional language to a more layperson-friendly language. What about natural language on the web? We have articles like this where you have to kind of extract information, not only about Erbitux help treat lung cancer, but really who was the author, when was it published, where was it published from. So those are also entities of interest. But then we have wild, wild west in Twitter and other social media, where you have tweets like this. I wonder if milk and honey thing works for heartburn because Tums is working for me. There is a medical kind of drug, Tums here, but there are also adverse events like heartburn, spelled wrong, and dietary supplements like milk and honey. So even this bit of this one tweet is giving you some information about possible adverse events from dietary supplement. Okay, so this task of identifying and extracting fields of interest or named entities from unstructured text is called information extraction. It comes in different forms. Different fields of interest could be depending on what data one is working with, whether it is clinical notes or tweets or prescription directions or web pages. So let me kind of quickly go through some of these. So cohort identification as first, where we use the narrative medical records to identify patients who meet certain criteria. It could be for clinical trials, but for other things. So for example, whether the patient meets or does not meet a particular criteria based on their longitudinal records, that means all of their records. Our first attempt on this was through a predefined task through the NLP clinical challenge, where the data set and task was very well defined, and there were diverse selection criteria that needed to be pulled out, including drug abuse and alcohol abuse and so on. And long story short, this kind of led to state-of-the-art results in the task, but really as a way to allow us to build natural language processing systems that gave us a broad understanding of different clinical selection criteria. What about risky alcohol use for patients? We kind of built on the previous work to then get NIH funding with my collaborator and multiple PI here with Dr. Anne Fernandez from psychiatry to create computable phenotypes of patients with risky alcohol use, where we kind of identify through text whether they are at low risk, no risk, high risk, or alcohol dependence because of risky alcohol use. And what we found was natural language processing of the clinical text helped identify 5 times more cases of potential high-risk alcohol use compared to just using ICD codes alone, just the administrative code information. And for drug use, it was 2.5 times more cases identified through natural language processing. In another project on identifying disease status of IBD patients, I worked with Dr. Ryan Stidham, who is a close friend and collaborator from internal medicine, to identify status of extraintestinal manifestations in patients with inflammatory bowel disease, where a typical note looks something like this, right? So again, this is again a synthetic example. Kerry also had long-standing history of severe enteropathic arthritis. This is the major complaint today, though luminal symptoms are not returned, right? Where that particular passage tells us that there is enteropathic arthritis and luminal symptoms are the two kind of concepts of interest, but arthritis is worsening. That comes to the second paragraph, where her joints and arthritis have worsened, whereas luminal symptoms are historical mentions. She has had them earlier, but they are not activating today. Moving on, what happens if we don't have any diagnostic codes? So how do you identify traits without any diagnostic codes? Where I'm collaborating with Dr. Randy Urban from University of Texas and Shu, who's going to be talking soon on phenotyping patients with brain injury, associated fatigue, and altered cognition, where really there are no diagnostic codes, but then we are able to use data from multiple institutions to find similarity in the clinical description and co-occurring codes to then help identify these traits. Through these examples, I hope I have kind of shown you that natural language can augment existing data and sometimes outperform just traditional diagnostic codes. Similarly, we kind of looked at how do you simplify prescription directions, where we used machine-assisted translation to go from the prescriber language to a more patient-friendly language through a combination of deep neural network models and some post-processing and normalization, by the end of which we were able to get the machine-assisted simplification to that could be used 94.3% times as is or with minimal changes. This is work in collaboration with my my two friends, Corey Lester and Yuan Jiang. Finally, I want to touch upon the promise of social media. Health-related communication has increased significantly, and laypersons share their information on social media, but it's messy, right? The grammatical structure might not hold. There will be a lot of typos, and it is not really natural language. It's short text language, where new acronyms and abbreviations come all the time. And you need to differentiate tweets that do talk about health information and those that just use the words, but are not really about the health information, as the second one here. So if you are able to overcome these challenges, then social media could still be used to augment information about adverse events that are there in our sources. So these examples of tweets kind of show that there appears to be some link, at least in the patient's minds, of Benadryl making them tired. And then we can check whether this NLP matches with what information we might have about Benadryl coming from other sources, other known sources, such as Medline Plus. I'm happy to kind of talk more about it, but to summarize, the examples that I have kind of chosen hopefully show you the variety of challenges that can be addressed by using natural language processing in medical information extraction, in simplifying prescription directions, and to understand community health. I would lead now to Shu, who is going to talk more about her own work and how once we have natural language processing understand the text, how it can be used in downstream tasks. Shu?
Thank you, Vinod. And thank you for the wonderful introduction. Let me share my screen first. Okay, so thank you for the opportunity to share some of my own experience of working with Vinod on hoping in the future we could extract information from EHR data, incorporating both structured and unstructured data, and also application of natural language processing methods to harmonize EHR data across systems. So I am a biostatistician at University of Michigan. And to me, when we talk about EHR data, in my mind, I think of it as structured and unstructured data, where for structured data, we're able to directly put them into one row per patient, one column per feature type of structure. Whereas for unstructured data, it includes clinical notes, narrative text, and medical imaging, where we would need, for example, methods like natural language processing to extract information. For example, we could look into visit notes and determine whether the patient's smoking status, which adds another column to my data set. And we could also look at radiology reports to decide whether the patient have any bone erosion. That's another column in my data set. Those kind of data can be then put into a machine learning algorithm as predictors for risk prediction as well as cohort identification. In addition to such rich phenotype data, there has been also a lot of efforts to link EHR data to biobank such that we can conduct both genome-wide association studies and phenome-wide association studies. So one such initiative really helpfully is at University of Michigan called Michigan Genomics Initiative, where we, so this is a study that enrolled patients from, surgery patients from Michigan Hospital, and patients would consent to share biospecimens for sequencing, as well as their current and future EHR data. And also they consent to be contacted for future studies. So this is really great data as it provides opportunity to study the association between many genotypes and many phenotypes. As of July 2021, we have more than 4,000 participants enrolled at MGI. So this is what eventually motivated my research. I wanted to develop statistical methods that can extract knowledge from EHR data that can lead to better care. And in the biostatistics and statistical world, there have been many fields that develop methods to analyze EHR data. And today I'm just gonna give kind of two examples. One is phenotyping algorithm, and the other is data harmonization. Okay, so for phenotyping algorithms, I'm gonna share a little not very successful story. So let me get started. So traditional rule-based phenotyping is the one that's most commonly used that derives phenotype for patients and relying on this clinical decision rules. Often it's in the form of a flowchart, and it incorporates both structured data and sometimes unstructured NLP terms extracted from clinical notes. The nice thing is that it's very simple to use and physicians can trace back, but the disadvantage is that it's sometimes hard to scale. It's not really scalable across conditions and institutions. On the other hand, this is the paper that I'm not part of, but I really wanted to utilize methods introduced in this paper called high throughput phenotyping with electronic medical record data using a common semi-supervised approach, FECAP. I really wanted to utilize methods introduced in this paper to conduct a phenotyping algorithm development study to identify patients with heart failure subtypes using MGI data. But my little story was at that time, we were really excited to develop methods and apply it to Michigan Genomics Initiative. But at that time, the unstructured data is not de-identified yet. So we're waiting for Vino's methods that allows us to get access to de-identify the clinical notes and to be able to combine both unstructured and structured data. But I'd like to talk a little bit about my dream of once we have both structured and unstructured data, how would we build up a phenotyping algorithm based on this paper? So here's a pipeline for this FECAP method, and it's also the general roadmap for majority of development of phenotyping algorithms. You will start from the raw EHR data and you want to filter patients into something called a data mart, where you have patients who at least have some chance of having the disease and also brings in sufficient information from their records. And then we will conduct something called feature extraction, where we extract from structured data into codified data and also from narrative text into NLP terms. At the same time, we would conduct chart review to generalize gold standard labels. It's a small set of yes or no, the patient have the condition. And then we would do, because it's a small amount of labels, we would like to do either there have been methods developed to conduct both unsupervised or semi-supervised methods for feature selection that allows us to reduce the long list of predictors into a smaller set for more efficient modeling. And then eventually after we build up the algorithm, we would eventually, once we select the predictors, we would build up a supervised algorithm and do training and validation using the gold standard labels. Throughout this step, the most exciting part and most time-consuming part besides chart review is feature extraction. So we're probably pretty clear about structured data feature extraction, but for unstructured data, we would really want to go into clinical notes and extract NLP data features. There are kind of three main steps if I were able to do it. We did work on it for mimic data, but not yet available at MGI. So the first step is to generate a NLP dictionary where we either rely on clinical expertise or look into Wikipedia or medical article to find synonyms of the phenotype of interest. And then we would parse clinical notes using NLP. This is not as easy as a find or search activity, but rather there might be negations, there might be family history, there might be different synonym of the same type of concept. So it's a really complicated method, and we would rely on experts like Vinod. And then we would obtain a so-called NLP term, which is count of positive mention of a specific concept in the patient's clinical notes. And then with those features extracted, that allows us to combine structured and unstructured data to build up phenotyping algorithms. And there have been a lot of studies that shown that the algorithm build up combining both structured and unstructured data performs much better than using medical codes and routinely collected patient characteristics alone. So that's my first little story. The second story I wanted to share with everyone is how to utilize one particular method in NLP to curate EHR data towards research quality. And I wanted to share a recent paper called "Everyone Wants to Do the Model Work, Not the Data Work." And this is particular work that I done. It's not model work, but rather the data work. Because if the data has poor quality, it would lead to a lot of data cascades in high stakes AI. So here's the problem I'm trying to solve. So we know that EHR data, they don't talk to each other because of financial incentives or synonyms or system heterogeneity. You could see that there's really, the medical coding has really been inconsistent both between healthcare systems and across time. For example, you could see that one system exclusively use one particular code, but never use the other code, and another system exclusively use the other code. And that happens across in both ICD-9 codes and CPT codes. In addition to difference between healthcare systems, you also see that we're currently using ICD-10 code, and we switched from ICD-9 to ICD-10 in 2015. And in a few years, ICD-11 is coming. So there have been a lot of manual curation and harmonization of EHR data, but a lot of them are not scalable and error prone. So what's the consequence to the different languages of EHR? Well, the consequence is that we frequently see that if you build up a phenotyping algorithm or statistical models using data from one particular healthcare system and you apply it to another system, the sensitivity and specificity will be dramatically dropped. And it's not a problem of the method, but rather a problem of the data, something that has to be taken care of before any statistical analysis is conducted. And here's what we did. In natural language processing, there's a method called word-to-vec, which basically represents a word in human language as a vector, and similar words are closer together in this language space. Now, if you think about every single healthcare system has its own language, and within this language, the medical codes are like words in human language. So we could readily represent medical codes as a vector, and from that, we can learn the coding practice in a data-driven way. And this allows us to do language translation. Suppose I learn the language between two systems, then I can harmonize this by creating a dictionary. Now, here's an example of what we did. We created such a dictionary using code translation, using NLP methods, and we mapped from ICD-9 codes from Partners Healthcare, which is a healthcare system in Boston, to VA. And we can see that it does identify codes that have very similar meanings, but have been used in very different ways across different systems. Another example that we did is we also generated word embedding using clinical notes in Mimic, where we found synonyms or names or words that's very similar to hypertension. And as you can see within the clinical note, you can find things like uppercase or lowercase HTN. You can even find things that are misspelled, like hypotension, HYPOTN, SION. So this word embedding method really is promising, that allows us to generate low dimensional embeddings from large scale EHR data, both unstructured and structured. So that concludes my two little stories. Lastly, I would like to acknowledge my collaborators, and this cannot be done without your help. Thank you for your attention.
Thanks, Shu. Just to kind of bring us back together about looking ahead and trying to kind of understand where we kind of take it from here, you notice that there is a need for kind of this informatics infrastructure, right? And that is why we are kind of talking about it in the context of this learning health system Collaboratory, where we have machine learning models, natural language processing models, and artificial intelligence-based systems that are gaining traction. But these methods are not 100% accurate. And there is a critical need to kind of explain these machine learning models. It's essential that we understand the biases that go into these models and how to overcome them. There are many clinical NLP tools available, but there is a need for dedicated effort to implement these in various settings. And I want to kind of highlight a partnership with University of Michigan's Data Office for Clinical and Translation Research and the Precision Health Initiative to de-identify the clinical notes at Michigan for research use. I know that there were already a couple of questions about these. We have a combination of multiple approaches for de-identification. One that's an in-house developed model called HIDEX, the hybrid model for de-identification and extraction. But we also use other approaches like filter that is used in University of California, San Francisco, and that's where I think one of our speakers are going to talk about it, and approaches of de-identification from MIT. And once we have these, build these computable phenotypes and making them available as knowledge objects becomes critical as part of the mobilizing computable biomedical knowledge initiatives. So the key takeaways is that NLP is an important tool in the arsenal to make sense of unstructured text, but it's also critical to kind of enhance the informatics infrastructure available to process textual data. Computable phenotypes provides a good basis as knowledge objects to be shared widely, and health-related social media can augment these efforts in determining social determinants of health and other uses. Thank you very much for this extremely short, but I think hopefully interesting introduction to natural language processing as I hand it over to Dave Hanover for talking about information retrieval.
Okay, great. Let me just find my slides here. All right, well, thank you very much. I guess we'll be doing questions later on because I saw that there were a few questions in the chat, but perhaps if we're a bit behind schedule, we will catch up on that. So I really appreciate the opportunity to talk about some of our work here and let people know about a related and perhaps somewhat different approach for utilizing and accessing the free text clinical data in our medical record systems. Now, let me just go to the next slide. The first thing I just want to mention very briefly is that if you want to take any notes or you're interested in any of these slides, the link at the bottom of this slide on the bottom right is where you can get these slides right now. It's at the bottom of every single slide, so you don't need to copy it down right now. You can copy it down as I'm going along. But the slides are there already. If you are interested in downloading them, you can reuse them, take pieces from them, whatever you'd like. Just a couple of disclosures here, some funding disclosures and disclosure about licenses and royalties about a large synonyms data set, which I'm not really getting into today, but I just wanted to list it there for completeness. Okay, the problem, free text. So it's already been sort of discussed a lot already about free text, but I really want to emphasize that free text is really quite complex. In many ways, the free text, unlike the structured data, is really a representation of human thought. It's really a representation of what the clinicians are thinking and trying to put down into writing what their thought processes are, what their concerns are, what they're sure of, what they're not sure of, and everything else that goes on. And because it really represents human thought, that's a really complicated thing to extract for a computer because computers don't, at least at this point, really understand or get human thinking. Another thing is that free text is a mess. I know it was mentioned last month that the structured data are a mess, but I would have to say that the unstructured data are probably even more of a mess. And I think Vinod showed some very good examples of that. Here's an example that I just came across, I think it was last week, where we have at least 100 patients in our medical record system that have domino pain. And it's not that their dominoes are in pain, but it's that someone either typed incorrectly or the transcription was wrong, where it was supposed to be abdominal pain, but it came out domino pain. And there's a lot of examples of that kind of stuff. Another problem is that the free text is very difficult to access. So many people just can't get their hands on these notes because they are usually locked down. There's a lot of security issues unless you de-identify them. It's hard for people to use them. And there's actually many reasons you don't want to de-identify them, because you have a large number of patients who you're trying to abstract data from for case report forms or looking for adverse events, where it's really actually important to know who they are. So in general, free text is sort of hard to use and hard to access in many ways. Another problem is that many of these free text tools are actually hard to use. Now, this is a paper, and guess what? The second author there is someone you might recognize. Vinod is on this paper, where they actually did a study about the usability of some of these software packages. And I just want to read one quote. The average ratings provided by the end user evaluators on ease of use and ease of interpreting output indicate that this group of users generally deemed the systems extremely difficult to work with. And that's not really meant to be a criticism of the tools, but just that they are very complex to use. And it's just really hard for the average researcher to implement or use these tools, unless of course you're partnering with someone who is an expert in NLP or data science or something along those lines. So a possible solution for these problems is a system that I would sort of call for the people. And when I say for the people, I mean something that's for the general researcher who is not a technical person, who doesn't have technical expertise and doesn't necessarily have a data science person on their team. So users, a good tool might be one that users can search the EHR on their own. There's no need to wait in a queue for an analyst or a data scientist, which is kind of very typical in many places. You keep the data secure within the centralized audited system, so there's no need to download or store the data anywhere else. You can sort of keep it within that system so that keeps it more secure. And as I sort of mentioned, easy to use for non-technical researchers. So our solution here at Michigan is a tool called Emers. Immerse is a search engine, so it's kind of like Google for free text medical record notes or documents. And the idea here is that a lot of people are familiar with Google already, so they're familiar with how that works, and that is really technically called an information retrieval system. Now, of course, Google is really far past simple information retrieval. They do have a lot of natural language processing and lots of very complex data models behind the scenes and how they do their work. But as a general idea, it's sort of thought of as an information retrieval system. And the idea is that it's really supposed to be very simple to use for research teams. This is software we've been developing and refining for about 16 years now. So it's really kind of been growing up and maturing over the last 16 or so years. So we've really been able to add new features and respond to our users to help provide more functionality and hopefully make it easier for them to use. It's a research tool. It's available at no cost. We make it available to people here who have the right privileges to access the data. And it's also available at no cost to people from other sites. So any site around the country that's interested in implementing this, they can get it themselves at no cost. It's an open source tool. And I will emphasize that picking the right tool for your research is really important. And often you do need multiple tools for whatever projects you're working on. Now, it is not natural language processing or NLP, but oftentimes you don't always need NLP, and NLP can be sometimes hard to use or customize unless you're Vinod or others like that. Many people just cannot use these tools out of the box easily. Now, there is somewhat of maybe people would think sort of a push and a pull of Emers or information retrieval tool versus NLP. I kind of think of Emers as what I would call human in the loop augmented intelligence. It doesn't do the work all the way for you, but it'll help you get your work done very fast, very quickly, but it still requires a person to help interpret some of the results and look at the context of where things are. NLP is generally more on the lines of artificial intelligence. It does things more automatically, but it does require also a lot of expertise and a lot of supervision as you're training models. And it can also make mistakes that are sometimes hard to predict or even identify in those cases. But I would say that really, in my view, Emers and NLP are really complementary systems. They can work together, and people should really be happy and not be fighting and arguing over these things. I think they can get together very well. Okay, what can you do with Emers? You can find cohorts based on things mentioned in the notes, things like diseases, drugs, symptoms, really anything that's mentioned in there, you can find. It doesn't have to be part of any standard vocabulary or ontology. It can be just really anything if you're interested in looking for it. It's great for finding things like rare cancers, and we will get to that in an upcoming presentation shortly. You can use it to highlight documents for chart review. So if you put all the terms in there, it will show you everywhere it finds it within the notes. So it helps you find things very quickly, even within the notes. We have this concept we call bundles, which is basically a saved set of search terms. Users can share it among their research teams, and it helps standardize the searches. It really helps support reproducibility. And some teams have even published these bundles or collections of search terms in their appendices of their papers, again, to help with the reproducibility, to show other researchers what the collection of terms were that they were using for the study. It's actually really fast because of the way it's designed. So if you do a search with a typical reporting database that might have the notes in the database, it's probably between 2,000 and 7,000 times faster than that. And because it's so fast, it really enables real-time querying. It enables a user to be able to modify their queries as they go along. Okay, what's the typical workflow of how someone might use this? Typically, you might, and this is not always the case, but you might start with a cohort identified using structured data, which was part of the discussion last month. You might use a cohort discovery tool, things like Data Direct here at Michigan, or I2B2, Leaf, or others that exist elsewhere. Then you might bring that list into Emers to look for additional details and abstract them, or look for things that might help verify or help you roll out certain things that might be mentioned in the notes. And then you may store those data in a electronic data capture system like REDCap, for example. We've had, as far as we know, about 450 papers and 82 abstracts that have used Emers. At least those are the ones that we can find that mention it or cite their work in the papers. And you can see a whole list of them at this link below. If you're interested in sort of seeing what they've done or what their methods are, you're welcome to take a look at that sometime. Where is the tool? Well, right now it's installed at about 4 places, and there's a handful of other places around the country that are currently working on installing it or are planning to, hopefully in the near future. Now, in terms of the future, one thing that we are excited about and we're working on getting to hopefully some realization of soon is what we're calling the Immerse Research Informatics Network. This really kind of is, again, for the people and hopefully for a lot of people across the country, real-time secure cross-site queries. The idea is that you can query among all the different sites in real time and get some numbers back in a secure way, not with any identifiers, no way to actually identify the patients, but some approximate numbers of how many patients have whatever you're looking for at each site, which might be really useful for finding cohorts for multi-institutional studies or other things along those lines. For more information, you can go to our website, project-emers.org. We have a lot of details there. We've got our documentation there. We've got lots of videos. The slides that I'm presenting right now are on that site already. And so you can get a lot of other details about what the project is about. If you want to, we do have a Twitter account for this where we tweet about different publications that have used the tool, about software releases, other announcements and webinars coming up. So it's sort of a way to follow what we're working on with the Emers project. And I do want to note that I want to thank our team, of course, for all they do for this. And if you're interested in contacting us, this is our generic team email, so it will come to all of us, emers-team@umich.edu. So if you have any questions, problems, want to know more, if you'd like a demo yourself, we're happy to provide you any of that information. And then really lastly, I just want to acknowledge all the different groups that have given us support over the years that have really made this possible, including multiple groups within Michigan, the NCI's ITCR, Informatics Technology for Cancer Research program, and of course, our users who really have helped propel this to where it is today. So I really want to thank everybody for that. And with that, I am done. So thank you very much. Now I see that there are questions in the chat, and I'm not sure if we're supposed to take them now or take them later.
David, I think we're going to take all the questions at the end.
Perfect. I'll stop. Thank you.
Okay. So we can move on to Leslie now.
Okay. Hi, folks. It's Leslie Yuan from UCSF. And I wanted to thank David for inviting me to present what's going on at UCSF. And I'm gonna, okay, hopefully you guys can see this. Okay, can you see my screen? I can't see you guys. So I'm assuming that's yes. Okay.
Perfect.
Yes.
Okay, great. So I work at the Clinical and Translational Science Institute at UCSF, and just a couple of disclosures and acknowledgements. We are grant funded. We also got a sub-award from Michigan in, I think, 2019. And this work at UCSF is a partnership between the CTSI and the Baker Computational Health Science Institute. So I just wanted to go back for a little bit of history. And what I'm going to be talking about is the implementation of Immerse at UCSF and how we're currently using it. So I went back through my emails and found the earliest email from 2016, basically, I think from David. It took us a while to sort of figure out how we could use Immerse, because we really wanted to. And I'm going to jump to 2019, where the folks at the Baker Institute were working on an algorithm that is called Filter for machine redacting the clinical notes. It was ready in 2019. We were able to make the decision to install an Immerse instance at UCSF against the machine redacted notes. So that was all happening in February of 2019. Then we were lucky enough to work with David in a partnership and receive a small sub-award from the University of Michigan for our team. Then COVID happened. We were in the midst of our implementation, and we decided to launch an additional COVID notes Immerse instance at UCSF to allow researchers to access that data. And again, for our instance of Immerse, it was really focused on supporting the research enterprise. We launched in July of 2020, and with 2 instances, the general Immerse instance that was around all the general notes, and a COVID Immerse instance. A note just about the machine redacting of the notes. The algorithm was not certified by our third-party organization and our privacy office as kind of certified de-identified, where people could use those notes without an IRB approval. So that was also kind of in the works. So while we launched in 2020 with Immerse against de-identified notes, you still had to have an IRB approval to access those notes. But now in 2021, I'm happy to report that the algorithm has been certified. We are rerunning everything, and hopefully before the end of this year, we're going to be reloading the certified de-identified notes into Immerse. And by early 2022, the researchers at UCSF are not going to need an IRB approval to use the Immerse tool. We're really looking forward to that. Let's see. So what we have today is over 105 million clinical notes for over 2 million patients. And the COVID set actually includes dates. So it is not fully de-identified, and there's about 260,000 patients. Apologies for the sort of old screenshot. I think we are running, I think, version 6.1. And the implementation of this software at UCSF was integrated with the single sign-on to make it easier for folks to access. So one of the bonuses that we sort of came up with here is in using Immerse and implementing it. The teams here had always really planned to provide programmatic access to de-identified notes to support the research. And by that, it's, software developers and David mentioned that the Immerse, user interface is really makes it available for non-technical folks. Our original plan for providing programmatic access was not actually working as well as we had hoped. And with working with Immerse and the Solar API that is sort of under there, we actually pivoted and are providing access to the Solar API for efficient and flexible text search for programmatic access. So UCSF users actually have access to the Immerse user interface and also the Solar API. So I'm going to sort of digress a little bit about the sort of de-identified data universe at UCSF. We have structured data that's de-identified. We are on the cusp of having certified unstructured, basically notes data that's de-identified. We are also working on de-identifying imaging data at UCSF. And we have a few query tools like Immerse, for example. We also have another homegrown query tool that allows importing and exporting of patient identifiers so that technical and non-technical users can actually look at the same patients across these different data sets that are de-identified. So I have a picture on the next slide here that kind of shows this better than I can explain it. But the patient ID is sort of the durable key that crosses all of these de-identified data sets. So the promise of actually enabling researchers to access these data without needing an IRB, because it's all de-identified, is coming pretty soon at UCSF, and we're really excited about that. So in terms of when I was preparing for this talk, I was talking with a variety of people who were using Immerse and trying to figure out how they were using it and what was happening. And what was great about talking with the various people was that it's being used by people who are highly technical and people who are non-technical. This tool has been really helpful for the first point, preliminary data review. Folks can look and pull up information very quickly, and it's important to do it before they spend time to write code to programmatically pull out data in bulk. Number two is in various previous slides that were shown, Immerse color codes different terms, and so the color coding actually permits people to see how many different colors actually can show up against different terms, which has been helpful. Quality assurance and training of data for deep learning models where folks are using it in the computational health sciences, discrepancies are easily reviewed by pulling up the notes. And then the self-service aspect of it, where really non-technical users can access the data on the de-identified side, but before actually going through the trouble of pulling data from identified sources, it has been very helpful. So I wanted to go through a quick sort of actual sort of use case. There's research going on to try to automatically classify breast images with a BI-RADS score. And the BI-RADS score is basically, you can see on the right here, a classification of the images for any findings. And the goal was to create a deep learning algorithm against the data that we had to automatically classify. And so the team basically, for step number one here, they used the clinical data warehouse, which is de-identified structured notes, identified the cohort, the unique patients with unique accession numbers for the exams. And using that cohort that they identified, they imported the IDs into Immerse to look at the de-identified notes that were associated with that cohort. And then in number three, they were able to validate and confirm via Immerse that these scores were in the notes, that they were used, where they were used and how they were used. And then using other Immerse features, they created term bundles, which were basically for BI-RADS 0 to BI-RADS 6. And again, with the different colors, they were able to actually very quickly see like a distribution of how those scores were across that cohort. And I think it basically validated and confirmed that the scores were being used in the notes and what they saw was expected. And then once the terms were confirmed, this team was able to create a direct query against the notes using the Solar API to export all of the data to use for this for training in this deep learning model. So, so in the end, we also have other areas, and these were just the ones that I kind of uncovered in preparing for this presentation of research that's being enabled. It's sort of across the spectrum from COVID to dentistry, nursing, oncology, ophthalmology. I'm sure there are many more, and we're really anticipating much more use of this tool once the notes are certified as de-identified. I had one quote that I wanted to read from one of our researchers who said, "We could kickstart the study by having a fast self-serve interface for looking at the data. If you don't know what's in the data set, it's risky to invest the time to pull it and write code to extract it. This is a really critical part of any study ramp up, in my opinion, looking at the data." And this researcher is thrilled to have Immerse at UCSF. I just wanted to end by thanking the University of Michigan Immerse team and show you the folks at UCSF who've been working on this implementation and the notes and the de-identification algorithm filter and some of the studies. And I think that's it for me. I am turning it over next to Christina, and thank you again for the time.
All right. Can you see my slides correctly?
Yes.
Perfect. Great. Well, good afternoon. I want to thank the LHS Collaboratory for inviting me to speak today. I'm a surgical oncologist here at the University of Michigan. My clinical practice focuses on melanoma and sarcoma. Sarcoma being one of the rare cancers that you're going to hear about today. I also took over as the director of the Sarcoma Research Working Group. So, improving research in rare cancers, especially sarcoma, is very important to me and all of us in the whole group and all my collaborators. So you will hear today about how we've used Immerse to help us on that mission. I don't have any conflicts. You can see my funding listed and honoraria for grant reviews. So rare cancers are defined by the National Cancer Institute of the NIH as fewer than 40,000 new cases per year in the United States. So this represents, if you put all rare cancers together, it represents 27% of all cancers. And, rare cancers significantly impact mortality in this country because it is 25% of all cancer deaths. So it is important to understand in research. Now, what are some of the issues with studying rare cancers? The golden standard, right, to guide evidence-based medicine is to have a randomized controlled trial. Well, in order to have a statistical significant result, you need a lot of patients, right? And so when you have very few patients, what happens, it's going to take more than 30 years to actually get any results. And so it takes an extremely long time and is really just unattainable. So low incidence leads to difficult end results. And so what we need is really well-designed retrospective studies that capture all patients of interest in order to do that. So when we try to do retrospective studies on rare cancers, we use the electronic medical record. You just heard a lot about different ways to mine the electronic medical record. And in general, to find diagnoses, you use ICD codes, right? And that is something that our cancer registry uses as well. Now, what's an ICD code? That's a billing code. Now, for rare cancers, one of the problems is they're not common, so they can be easily mislabeled. The names can change over time, which drives all of us crazy, but it happens. An example is malignant fibrous histiocytoma. So this is a type of sarcoma. In 2002, the World Health Organization decided that we needed to change the name because of the histology to undifferentiated pleomorphic sarcoma. However, pathologists at different places, different pathologists, different institutions might call it one or the other. And so then that actually leads to issues when you're trying to actually have a diagnosis. And we'll get to that when I show you how these billing codes work. Another example is well-differentiated liposarcoma. So this is another type of sarcoma. It actually is the exact same thing as atypical lipomatous tumor. Those two entities are exactly the same, but they are called two different things. Again, depending on the pathologist or depending on location, some people will call it ALT if it's in the extremity. They'll call it well-differentiated liposarcoma in the abdomen, and then some it's a mixed bag. And there's also location-specific coding. So all of these things lead to a lot of problems with finding sarcomas using ICD codes. Now, let me just give you an example. Let's say we want to go and look up atypical lipomatous tumor, or let's say there's a new coder who's trying to code this, right? They see it in the pathology report or they see it in the surgeon's note and they want to look it up. Well, if you look up atypical lipomatous tumor, you end up with an ICD code that has nothing to do with liposarcoma, right? You have lipomatous, you have atypical, you have skin, none of these things. This is all benign. And actually an atypical lipomatous tumor is a malignancy. So there's one problem. Now, another issue with just sarcoma in general is sarcoma are cancers of the soft tissues, but there are more than 70 histological subtypes. And they all have different biology and they act different. And if you're going to do a study and you want to look at one of them, if you put it in a mixed bag, you're actually never going to get any really good results. Okay. Now, the ICD-10 billing code for sarcoma is by site. So I'm going to give you an example. You have an atypical lipomatous tumor, right, which I told you is the same thing as a well-differentiated liposarcoma of the arm. This is coded as C49.1, which is soft tissue of the upper limb or shoulder. I can tell you a well-differentiated liposarcoma acts extremely different than a malignant peripheral nerve sheath tumor, which has metastatic disease that's about 50 to 60% of the time, where it's almost zero for this entity. So you can't put them in the same bag if you're going to study them. So we use an additional histology code, but again, if someone was trying to find a code for this, if they only saw atypical lipomatous tumor, what are they going to put it in? They're probably going to put not otherwise specified, which is incorrect, okay? Because there's other types of liposarcoma that act very different than this. So again, just to give you an example of how, if you just wanted to pull codes out of the medical record for a study on one of these things, that you might actually miss a lot of patients. So if you say, I want code 88513, you might miss all the atypical lipomatous tumors that were coded in another bag. So I'm going to give you an example of my experience using Emers. This is a research project that I did. I was the faculty lead of a group of medical students. So these are second-year medical students as part of the surgical scrubs. It's like a summer research program. And to give you an idea of having, right, second-year medical students, none of us were data scientists, right? And to approach a clinical question in using Emers. So cutaneous leiomyosarcoma is a type of sarcoma of the skin. All right, it's a very low incidence, and there's actually two different kind of types based on histology or pathology. One is just in the epidermis, the other one goes down through the dermis into the subcutaneous area with extension. And we thought, hey, do these behave the same? Are the ones that extend down, are they more aggressive? Not a lot of data. If you try to look into the public, at the time, if you looked in the published literature, there were a handful of studies with like less than 50 patients each, most of them like 10 patients, case reports with 4 patients, okay? What we do know is that subcutaneous leiomyosarcoma, so again, location-specific biology, not involving the skin, these are a very different disease, okay? The distant recurrence in from metastatic disease is 50 to 60%, where it was extremely low that we kind of knew, and from case reports and just from, clinical experience, that this was much lower. But a lot of clinicians will treat cutaneous leiomyosarcoma the same, just because they see that scary sarcoma word, okay? No clinical guidelines. There was no NCCN clinical guidelines because we don't have enough research, right? So what we wanted to set out to say, okay, let's better understand these diseases. Is there a role of imaging? Do we even have to look for distant recurrence in these cutaneous leiomyosarcomas? And is there a difference in recurrence between those with extension and not? So the group of students set out, and the first thing I did is I said, hey, cancer registry, I want to look at cutaneous leiomyosarcoma. So how did they do that? So they went to the ICD codes, they pulled out soft tissue sarcoma, they pulled out leiomyosarcoma as a histology, and we went through sites, and we went through those, and we ended up finding 101 patients through that list. And then one of the students, so we have the student here, Bhattacharya, who said, hey, let's use Emers. He's the one that introduced Emers to me. He'd worked with Dr. Hanauer. And so what I did is we set out and we used cutaneous leiomyosarcoma, dermal leiomyosarcoma, so synonyms. And what we first pulled out actually was 311 patients. We'll talk about why it was so high. And then when we went through those, we ended up with 128 patients that were truly found to have cutaneous LMS after we did manual chart review. And so if we only used the cancer registry, we would have missed 21% of patients. Okay, so you can see when you have a rare cancer with small amount of patients, that's a big difference right there. Now, when we talk about, so why did we have these first initial false positives? So we've learned subsequently that there's a way to kind of make this a little bit more efficient. There were some patients who had seen a genetic counselor for a genetic mutation that never had a diagnosis of cutaneous leiomyosarcoma, but in the text of their consultation note was a risk for having cutaneous leiomyosarcoma. So now that I know, and in future searches that we're doing, there's a feature in Immerse where you can exclude certain text to reduce that kind of false positive. So this, our approach and our results was presented as an oral presentation at the Association of Academic Surgeons earlier this year by one of the medical students. So our next, approach was to look at, so what about resection margin, right? No clinical guidelines. So if you look through, some patients would get 1 centimeter margins around, to cut this out, 2 centimeter, 3 centimeter, it's all over and there's no clinical guidelines. So we wanted to say, hey, does it make a difference? Is the recurrence difference depending on margins? So our students used Emers to look through, again, the free text, looking for margins in the operative report. And then recurrence based on imaging and clinical exam as well. And these results were presented as a poster presentation, the Society of Surgical Oncology last March. We were able to identify the different subtypes and also look at the different margins. And so all the different criteria that we wanted to look at, the students did a great job putting together. And I'm just saying, the punchline is extent of margin did not affect local recurrence. Okay, so that's really important. So now, depending on the subtype, whether it has extension or not, we still don't recommend doing, wider margins per se. And another thing that we looked at was imaging, right? How much imaging should we do on these patients? I told you that we didn't think that the patients with this dermal only type of leiomyosarcoma would have any kind of distant recurrence, but we said, well, what about the ones that maybe are more aggressive? So again, the students using Immerse went through all the radiology reports, collected all the imaging. And, if you can see here, essentially the patients that had only dermal, contained to the dermis, their imaging detected recurrence was only 1%, very low, but look, it went up to 80% if it had subcutaneous extension. And then confirming, we know the ones that are subcutaneous were much higher. We already knew that, so that was confirmed. But here we can say that maybe the ones with subcutaneous extension should have. Now, we're still talking about low numbers. Again, I told you we can't just low numbers, but this is a perfect kind of example of how we use Emers to get a larger number that had ever been published before. But just like you heard about the different institutions, if we now could use this exact same way to identify patients, and we did it in a multi-institutional study, some of the other institutions that had the ability to use Emers as well, we can likely increase our numbers quickly and do some collaborative research. This was presented as an oral presentation, and it was actually selected as the best of SSO and was put together as a webinar and distributed internationally. So the students were very excited about that. So here's an example of a group of students that hadn't done research before using the tool of Emers and then putting together 3 presentations and doing a great job. And actually, it has changed some of the way we approach our clinical care here. Another example that's not necessarily rare cancer, but in my lab, I do translational basic science research. So I just want to give you a little idea of how I use it in other ways. So we know that patients that have metastatic melanoma, a lot of them are treated with immunotherapy. So these are new treatments that really just came out in 2011 that boost one's immune system to fight melanoma. And we went from having almost no treatments, essentially no treatments that improve survival, to now we have up to about 40 to 60% of our patients with metastatic disease will have long-term survival. It's amazing, okay? Now, one of the things that's really cool is that one of the side effects of immunotherapy is these patients can get something called vitiligo, where their immune system actually kind of breaks down the melanocytes and they lose pigment. And we know that if patients develop this, their survival is much longer than others. So a cool thing. So of course we want to study these patients. So in my lab, we take biopsies, skin biopsies of these patients, and along with their tumors. And I'm not going to go through, this is not a basic science talk, but we go through a whole process to actually look at the T cells, okay, in these tumors. Now, why am I bringing this up? Well, how do I find these patients, right? Their side effect of vitiligo is not coded as a diagnosis. It's something that is seen in the clinic and ends up being something that is reported in a note. Okay, so you can't find an ICD code of vitiligo in these patients. And I need these patients in order to do my studies and clinical trial. And also for numbers, like if I'm going to put a grant in for my next grant and I have to say, hey, how many patients at the University of Michigan actually have this side effect that I can study? I need to know those numbers. So I went to Emers. Now we have a data set of all of our patients that are on immunotherapy. So since we started giving dual therapy to our patients, I had a data set of 383 patients that I already had, and I uploaded it into the Emers system. Okay, so here's my data set. You can see I have other data sets. Here's just one of them that I use. And then I looked at my search. So I put in vitiligo. Cool thing about Emers, it then's like, well, here's some synonyms. And one of my favorites is here's some other misspellings that typically happen. So let's add that too, so we don't miss them. And as I did that, you can see that the patients pop up and they highlight the notes that have vitiligo in them. And so after I went through and did the chart review of that, I identified 95 patients that had immunotherapy-induced vitiligo. Now, 120 charts came up, and it was because about 25 patients had, again, vitiligo listed as a possible side effect during a consultation with a medical oncologist. So those I excluded and ended up with 95 patients that now I could find and target for my study. So a great way to efficiently find patients to do my translational research as well. So I'm going to end there. I want to thank, so here's my laboratory team. And this is Cameron Harder, is one of the medical students that does a lot of this translational work. She's done 3 other studies with me actually in sarcoma using Emers. And so we're all big fans. Happy to take any questions.
Thank you so much, Doug.
Okay, I think we can get into the questions now. My video is muted, I see, but I have a picture up there that looks better than I look, so I'm going to settle. We have a number of questions that were able to be answered by the panelists, and those questions are mainly technical questions, and you can refer to those answers in the Q&A. So what I'm going to do is I'm going to focus instead on the open questions that still remain. One of the first of those is a question about the NLP software that we've used for our studies. So go forward and give me an answer to that. Give an answer to that.
Thanks, Doug. Yes. So at Michigan, we do experiment and work with multiple NLP softwares. We have a kind of a playing ground, software kind of space, kind of a sandboxed environment where we try out different approaches that have been published earlier and toolkits that are available. So specifically, there are multiple natural language processing pipelines. So for example, you could think about it as the UMLS meta map as a pipeline, or CTEX as a pipeline, or the ones that have been kind of proposed from Mayo, so MedTagger and so on, in addition to our own in-house kind of developed models. So that's kind of a more generic answer to different software, NLP software tools that are used. The ones that are kind of highlighted are mostly based out of Michigan Medicine, and hence they have a combination of pre-processing tools that are tuned for Michigan, followed by these NLP tools.
Okay, and a second question is, do we have experience at the University of Michigan with mentorship teams for career development awards that are focused on NLP?
I think the best way to answer that question would be for Tyler to reach out or email, and kind of we can find out based on your expertise in the area that you are working on, to see whether mentors could come from domains of interest or methodology. So please reach out through email. I can put my email address in the chat.
Okay. Interestingly, we have a participant from Agra in India who's interested in prescriptions, and we've provided some answers already to some of his questions about technical issues, but he has some broader questions here. One is there a pharmacy learning system operating anywhere in the world? So I've opened that up to everyone on the panel.
I could start with some of the work that he was kind of talking about, but then I do think that this is a question that I think a lot of our panelists can jump in. So just to get everyone in the context, kind of to get everyone on board, what Mayank is kind of highlighting is the fact that there is no specific prescription management software or systems like SureScripts or similar that we have in the US. So prescriptions are kind of written out in paper and kind of handed into to pharmacies. And so the question, I think, kind of comes from there. Is there a way to kind of have technology that can take those and then convert them into structured prescription for patients? So to answer that line of question, I think to generalize it a little bit, we have been kind of talking a lot about natural language processing and text data, where things are already in the computer system in text form. But it can happen that sometimes it comes in as images, for example, scanned copies of PDF, and in Mayank's case, it would be OCR, a scanned copy of a written prescription, which then has to be OCR'd into the health system. So when that happens, there are tools available to convert images written form into text. They are not the most accurate of the world, but things are improving in that space. So sometimes when data comes in non-text format, they could be converted into text stream, and then you have kind of build in specific tools to then convert it into structured prescriptions, as we had talked about. So broadly, Mayank, I think the answer is it has to be a very specific kind of implementation that suits the needs of the project. And I'm kind of we could chat about it offline too. So I do encourage you to kind of reach out to me. There are some initiatives that we have for the global audience and the global health, and I think this one definitely fits that role. On your question about pharmacy, learning health system, and vision, Chuck, go ahead.
Yes, Vinod, I was going to say we have you've given a wonderful comprehensive answer, and I know you'll be in touch with Mayank. So we have a couple of questions and only a few minutes left that pertain specifically to Immerse, and I'd like to get to those. Excuse me for jumping in. So we have a question that asks, does Immerse include protected notes such as those from psychologists? David, or any of the Immerse people?
It's a good question. I would imagine here at Michigan it probably does, because I think there was an intentional decision to make sure that those were also available to all other clinicians for clinical care or research. But at the same time, I would say that most of the notes that we get are through a process that first sends the notes to the health information exchange that we belong to. So if they are not sent to that HAE or health information exchange, then we probably don't get them. But if they are being sent there, then they are probably included there. And if you have more questions about that, just contact us and we can look into it and get you some more answers. But that will all depend on each specific site's implementation, because everybody has their own rules.
Okay, thank you, David. Then there was another question about Immerse. I don't see it here at the moment, but it was a very good question. So,
I may have answered it in the already, so that may
okay, but let me put it to you as well. This is the question about what is the lift for deploying Immerse? Is that the question?
Right, yeah,
So-
I mean, that was one of the questions that just came about. We actually have some documentation about that. Lisa Ferguson, who is on the call, but I don't know if she can talk, we have good documentation about that. In general, the actual implementation part is not very difficult, but working with your site in terms of figuring out how you're going to get your notes and getting all the permissions in place, that's the hard part. So it's not technical, it's all political. Maybe Leslie can also comment on that, because remember that we first were in touch in 2016. So you want to say anything about that?
I would totally agree with that. And I don't think the technical lift, we had, 2 folks that were, sort of part-time on it. We're happy if anybody wants to reach out to the UCSF team on what happened over here. We're happy to talk to anybody who's interested.
Okay, thanks, Leslie. We have another question about the F1 scores. What do they look like for Immerse?
Well, we don't really do things that way, because again, this is sort of the human in the loop kind of process. But what I would say is that we have actually, or I have benchmarked it against some prior I2B2 challenge data. We haven't published it at all, but in general, it really works pretty well. And I have some issues with the way that the scoring is done for some of these challenges, because they're pooled answers. So we found, when I used the Emers system, we found responses that look like they're really correct answers that were not a part of sort of the official gold standard. But if we ever get a chance to publish that, we can provide that information. But in general, the idea is to present this to the humans, the users, and let them make the decisions about their interpretations of the results.
You might want to say what an F1 score is for some of the folks out there.
I would like Vinod answer that question. He will be the expert in that.
So F measure is the harmonic mean, which is a form of kind of averaging sensitivity and positive predictive value. So both have to be high for F1 to be high, and it goes from 0 to 1.
Okay, so let's see what we have time for. One more question. I think we've exhausted the questions that have not already been answered in the Q&A. Would anyone like to unmute and ask one last question before we call this 90 minutes very well spent? All right, well, not hearing anyone, I just want to say that Doug had some kind of household matter arise that took him away. That's why I finished up the Q&A, but thank you for attending. There is a post-event survey that will be available to you, or the link will be available to you as you exit the webinar. I believe we had about 150 people here today, which is a very, very nice turnout and exemplary of not only the interest in this topic, but also the interest in our terrific presenters. And I'm sure nobody was disappointed by the excellent presentations that we had today. A link to the webinar materials will be placed in the Collaboratory website archive, and you see the URL for that there. As was noted in the pre-session slide loop, we're going to be very excited to welcome Julia Adler-Milstein, again from UCSF. And she will be speaking on another data-related concept on which she is probably the world's expert, the current state of interoperability and its implications for learning health systems. That's data interoperability and implications for learning health systems. We will be sending out registration information for that webinar soon, and we look forward to you all joining us then. So thank you very much for attending. Thank you so much to our speakers. These were such wonderful, informative, and also entertaining, I should add, presentations. You had me on the edge of my seat, and I'm sure that was true for everyone who was in attendance today. So thank you again. Goodbye. Have a terrific rest of your day.